Thank you for joining us on Synthesis Workshop. In today's installment of our Advanced Organic Chemistry course, we're joined by Dr. Stephen Crossley. Stephen will include some of his biographical details in his talk today, but I'd just like to mention that if you enjoyed today's talk, be sure to check out Stephen's previous talk on this channel, where he discusses his total synthesis of picrotoxin and picrotin from the Shenvi group. Today, we begin our synthesis module of the course, and to do that, Stephen will be giving us a talk about retrosynthesis. With that, I'll hand it over to you, Stephen. Thank you for joining us.
Hello. Thank you for tuning in. It's my pleasure to present a tutorial on the topic of retrosynthetic analysis. In the words of Professor E.J. Corey, retrosynthetic analysis is a problem-solving technique for transforming the structure of a synthetic target, or TGT, molecule to a sequence of progressively simpler structures along a pathway which ultimately leads to simple or commercially available starting materials for a chemical synthesis. Graphically, this can be depicted as reducing the molecular complexity of a target molecule through a series of synthetic steps until one arrives at simple or commercially available materials. My goal with this tutorial is to introduce retrosynthetic analysis at a graduate level with a focus on how to identify strategically simplifying disconnections, as opposed to covering the vast majority of tactical means for enacting a given set of disconnections. For a more detailed discussion, I would refer you to Corey and Cheng's seminal text, The Logic of Chemical Synthesis. My own background and training is in total synthesis and synthetic methodology, and I'm fortunate to be able to apply these principles of retrosynthetic analysis in my work as a process chemist. As a disclaimer, this tutorial is for educational purposes, and any errors, omissions, and opinions expressed herein are my own only. For your reference, here's an outline of this lecture. To start, I think of retrosynthetic analysis by analogy with chess as having strategic and tactical elements. In my mind, strategy in chemical synthesis involves identifying the most simplifying ways to disconnect a molecular structure, while tactics are the individual chemical steps or reactions used to make chemical bonds in the forward direction. In other words, strategy identifies where to disconnect chemical bonds, while tactics involves how to form bonds in the forward direction. Therefore, although strategy and tactics are interdependent, strategy is foundational and should be used as a guide in the selection of tactics. Corey taught that molecular complexity should be used as a guide to identify optimal bond disconnections. Once identified, one can use knowledge of chemical reactivity and chemical reactions to select specific bond-forming reactions. For example, I like to think of tactics based on specific mechanistic regimes, such as polar, radical, pericyclic, and organometallic, and based on known chemical reactions, such as those known from named reactions. It's also worthwhile to note that prioritizing optimal bond disconnections provides an effective way to identify opportunities to invent or discover new reactions or reactivity. If a bond disconnection is strategically optimal, but there are no known reactions which can form that bond in that context, it may be a good candidate for a synthetic methods development project. Okay, before I discuss molecular complexity in more detail, there are several key terms used in retrosynthetic analysis which I want to go over. First, a synthetic target, or TGT, is the molecule under retrosynthetic analysis. A disconnection is a retrosynthetic step involving the breaking of a bond to form two or more synthons, where synthons are the conceptual fragments corresponding to a synthetically tractable chemical structure, or synthetic equivalent. One obtains synthons and synthetic equivalents by application of a transform to a target. A transform is the exact reverse of a synthetic reaction, that when applied to a target gives reactant structures. In this example, application of a Claisen transform to this synthetic target gives an enolate and an ester. Another key term is a retron, which is the minimal substructural element in a target structure which keys the direct application of a transform to generate a synthetic precursor. Chemists tend to use retron and keying element interchangeably. One can also identify partial retrons, which can be converted into a retron by application of one or more additional transforms. In this particular example, the 1,3-dicarbonyl highlighted in red is a retron for a Claisen reaction, just as a 6-membered carbocycle containing an endocyclic alkene is a retron for a Diels-Alder reaction. Finally, a retrosynthetic or X target tree, X because it grows out from a target, is a branching tree structure formed by retrosynthetic analysis of a target molecule with nodes which correspond to structures of intermediates along a synthetic path. In this example, breaking bond A versus bond B leads to different synthons, though very similar, and the synthetic equivalents of these can then be evaluated for the relative merits. In this case, one might consider the relative merits of having an acidic proton in the electrophile, disconnection A, versus the necessity for stereo-controlled enolate formation, disconnection B. Of course, the more complex the target is, the larger and more branching the retrosynthetic tree can become. This is an example of a few branches of a retrosynthetic tree presented in Corey and Cheng's text for this molecule. One should build retrosynthetic trees by iterative application of transforms to generate subtargets, and the relative merits of individual pathways can then be compared. It's always important to identify your goals in synthesis. Some common goals are to produce material for biological studies, characterization, diversification, etc., to explore and/or discover new chemical reactivity, to benchmark state-of-the-art methodology, tactics, and/or strategies, and to train students in the design and execution of multi-step organic synthesis. While your particular goals will inform which routes or intermediates are prioritized, in general, shorter routes are preferred and enable these goals. Stated another way, short routes maximize the slope in a graph of complexity versus step count. Therefore, to effectively maximize this slope, we need to identify component elements of molecular complexity and priority rank transforms based on how effectively they build up molecular complexity. That requires us to answer the question, what is molecular complexity? Corey lists 6 key contributors to molecular complexity in his text, namely molecular size, cyclic connectivity or topology, element or functional group content, stereocenter content and density, centers of high chemical reactivity, and kinetic instability, especially thermal. Most of us have an intuitive sense of molecular complexity. For example, if I were to ask you to rank these 3 natural products, dopamine, vilmorconitine, and vancomycin, in terms of relative complexity, how would you rank them? Most likely, you would rank them as increasing from left to right. We can rationalize this intuitive ranking using Corey's component elements of molecular complexity. Molecular size increases from left to right. Cyclic connectivity, or topology, is more challenging though. Both vilmorconitine and vancomycin are more complex in this regard than dopamine, but vilmorconitine has arguably higher topological complexity than vancomycin, due to it having a larger variety of ring systems, including fused, bridged, and spirocyclic. Vancomycin, however, has multiple macrocycles. In terms of element and functional group content, all 3 molecules have carbon, hydrogen, oxygen, and nitrogen atoms, but vancomycin also has a chlorine atom, and the absolute number of heteroatoms increases from left to right. Vancomycin also possesses the highest variety of functional groups. Vancomycin is the winner in the stereocenter content category, possessing both axial and point chirality, while dopamine is achiral. Vilmorconitine, however, does have a high density of stereocenters. Centers of high chemical reactivity and kinetic stability can be harder to identify because they depend on context. In an argon atmosphere at negative 196 degrees Celsius, few molecules would show any reactivity, but under an aerobic, humid atmosphere at room temperature or higher, many events become possible. Most common degradation pathways involve oxidation and hydrolysis. Spontaneous aerobic oxidation, such as that of a diphenol of dopamine to the corresponding orthoquinone, or oxidation of amines to nitrosamines, become possible, while hydrolysis of esters, amides, and thioesters may also occur depending on the temperature and water content. Molecules with high-lying HOMO orbitals like phosphines or polyene, phenolic, and pyrrolic natural products are susceptible to oxidative degradation, while molecules with low-lying LUMOs are susceptible to nucleophilic degradation pathways. Centers of high chemical reactivity and kinetic instability can be identified as well based on relative ground state destabilization, such as in the case of strain structures, which lead to various types of strain-releasing rearrangement pathways under Bronsted or Lewis acidic conditions. You can imagine how ranking these features, relatively speaking, could be challenging. Fortunately, there have been efforts to quantify molecular complexity within the chemoinformatics community. Thomas Böttcher has developed a quantitative additive complexity index, denoted CM, for structural complexity, which accounts at least for the first 4 features of Corey's component elements of molecular complexity, using degrees of freedom as one factor. The Shenvi and Wiley labs at Scripps have made a free calculator where you can plug the Smiles code of any given molecule in and obtain a Cm value. A Smiles code can be generated in ChemDraw by selecting a structure and then going to the Edit and Copy As options in the menu. When we plug the Smiles codes for dopamine, vilmorconitine, and vancomycin into the calculator, we see that the absolute structural complexity indices do indeed match our intuitive ranking, increasing from 114 to 468 to 1844. However, notice that vilmorconitine is ranked as slightly more complex than vancomycin on a complexity per atom basis, reflecting its high topological complexity and density of stereocenters. All this discussion of molecular and structural complexity is important because molecular complexity serves as a guide to determine which bonds are best to disconnect. To design a short synthetic route, we need to identify and prioritize routes which build up complexity in as few steps as possible. Okay, so how do you prioritize among various possible bond disconnections? We can broadly classify transforms into 3 levels based on how they affect molecular complexity. First and foremost are complexity-building transformations, those which make new chemical bonds and/or stereocenters. Examples of high-complexity building reactions include cycloadditions, manic reaction cascades, cation polycyclizations, and transition metal catalyzed or mediated cascades, for example. Transforms which form multiple bonds and/or stereocenters in a single reaction are especially powerful. Second, lateral transformations are those which have a minimal effect on the net change in complexity. Examples include rearrangement reactions like sigmatropic rearrangements or functional group interconversions like the Payne or Stevens rearrangement reactions, in which bonds or stereocenters are transposed or reconnected, but the molecule does not experience a net increase in complexity. The third and least desirable class of transforms are concession steps, which involve addition of functional groups not present in the final target, such as protecting groups, or redox manipulations, which add steps without increasing the overall molecular complexity. These transforms should only be used as a last resort and whenever possible circumvented or removed. Graphically, complexity-building transformations have a positive slope in a graph of complexity versus step count, while lateral transformations have a slope of roughly 0, and concession steps have a net negative slope. Remember, our goal is to build up molecular complexity in as few steps as possible, and so complexity-building transformations should be prioritized, and the latter two, lateral and concession steps, should be used only insofar as they enable complexity-building transformations. With these fundamental concepts under our belts, how does one practically apply these principles to triage which bonds to disconnect? Well, since highly simplifying disconnections retrosynthetically remove elements of high complexity, foremost among these being stereocenters and CC or CX bonds, the way I go about retrosynthetic analysis of a given synthetic target is first to identify stereocenters, identify CC and CX bonds to stereocenters, and then, if there are ring systems, to identify bonds which connect those ring systems. It follows logically that transforms at the intersection of these points of complexity will be even more powerful. Once these points of complexity have been identified, use them as a starting point to search for tactics which can form the relevant bonds as expediently as possible. Among complexity-building transformations, if you can find reactions which form multiple CC or CX bonds simultaneously and/or stereocenters in a single step, all the more power to you. Okay, let's apply these rules to some natural products. Here are 4 similarly sized natural products: ostamide A, viresane B, curvulamine, and pipertoxinin. Plugging their Smiles codes into the Böttcher calculator yields the complexity indices shown. So you can see that they all have similar structural complexity at an absolute level, with ostamide A being the least complex on a per atom basis and viresane B being the most complex on a per atom basis. Next, we identify points of high complexity. Our first step is to identify stereocenters. I've circled sp3 stereocenters here, but one should also include EZ geometric isomers and atrop isomers when relevant. You can see that there are 3, 7, 6, and 8 stereocenters respectively, moving left to right. Second, I identify CC and CX bonds to those stereocenters. Seek to either preserve these in the starting materials you select or find tactics to form these bonds in a stereo-controlled fashion. Third, in molecules with multiple rings, identify small to medium ring systems. Bonds connecting intact medium rings are usually strategic. Often, one can develop convergent routes which bring together 2 halves. After candidate strategic bonds have been identified, construct retrosynthetic trees around the strategic bond disconnections and use Corey strategies to narrow down the practicality of possible routes. Corey's strategies are, first, transform-based strategies, which use retrons or partial retrons within a target structure to identify highly simplifying transforms. Stereochemical strategies, which are those that remove stereocenters and stereo relationships under stereo control. Structure goal strategies, which identify a particular substructure to focus retrosynthetic analysis. Use of chiral pool materials is a common and powerful example of this. Functional group strategies use functional groups to guide the retrosynthetic reduction of molecular complexity. Examples include recognition of matched, mismatched, and consonant-dissonant relationships between functional groups, and reduction of oxidation patterns to alkyne, alkene, and alkane precursors. Finally, topological strategies use a particular bond, pair of bonds, set of bonds, or subunit as eligible for disconnection or preservation to guide retrosynthetic analysis. Corey recommends concurrent application of all of these strategies to find a short practical route. Now, let's apply these principles to some molecules. First, we have austenite A. Identification of the strategic bond suggests that the bonds between the vicinal stereocenters is the most complex, but all the bonds highlighted in green and blue are strategic and candidates for disconnection. There are 5 ring systems in this molecule. From the standpoint of convergency, it would be best to forge ring C from the merger of the AB and DE ring systems, which would then become sub-goals for further analysis. Next, we should consider Corey strategies and ask ourselves relevant questions such as, what retrons or partial retrons can facilitate strategic bond formation? How can we form the stereocenters with stereo control? Are there chiral pool or other easily made or commercially available substructures embedded within austenite A? How can we use functional groups present within austenite A to make strategic bond disconnections? And which rings make the most sense to form, and which make the most sense to preserve? When I think through these questions, the structured goal strategy leads me to recognize that austenite A contains tryptophan, dihydroproline, and butanol moieties. This also means that we can preserve rings A, B, and E, which is consistent with our initial identification of strategic bonds. Then, with these starting materials identified, we can focus on searching for tactics to form specific bonds. The lactams can be formed via amide coupling reactions, but the most challenging bond to make is that of the vicinal stereocenters. A search for retrons identifies the alpha-alkyl ketone highlighted in red as a retron for a semi-pinnacle rearrangement, a transformation that is known and utilized in these kinds of indole natural products. Alternatively, one could consider inverting the reactivity of the butanol moiety through use of a hydrazone or via chiral enamine catalysis, or seeking to effect an alkylation with an allylic boronic ester. The relative merits of these potential routes could be compared and may ultimately be evaluated experimentally. Next, we have Viracene B, which is a stereochemically dense and topologically complex natural product. Analysis of the strategic bonds for disconnection identifies that there are 7 contiguous stereocenters highlighted in red, which yields a large number of candidate CC and CX bonds for disconnection. It also has 5 or 6 member ring systems. And so, again, application of Corey strategies can help us narrow down the plethora of potential retrosynthetic disconnections. Immediately upon asking the first question, what retrons or partial retrons are present, the one retron which stands out in this molecule is the 5-membered ring containing an NO bond, highlighted here in red. This structure is a keying element for a 3+2 dipolar cycloaddition, which would build 3 sp3 stereocenters and form 2 strategic bonds in one step. Application of this 3+2 transform therefore yields the molecule shown. Use of a functional group strategy, via application of allylic oxidation and imine N oxide formation, yields the 430 bicyclic ring system shown, with an attached pyrrolidine moiety. The attached rings could potentially be forged via a stereoconvergent nickel-catalyzed decarboxylate of cross-coupling between Bach-protected proline and a butenolide synthon, which could in turn be made potentially via a Pelson-Kahn reaction and an oxidation. Alternatively, the central intermediate contains a retron for a Diels-Alder reaction, although electronic considerations, such as that of both the diene and dienophile being electron-rich, and the relative difficulty of forming a diene which is out of conjugation with an ester would likely render this disconnection tactically ineffective. Much harder to see objectively, but something that was known to those familiar with these natural products is that allonorsecurenine is thought to be a biosynthetic precursor to viracyne B. This structure-goal strategy leads one to recognize that allonorsecurenine can be converted to the imine N oxide intermediate by application of Meisenheimer and Polanovsky rearrangements. Allonorsecurenine, in turn, contains a full retron for an E9 metathesis reaction, which when applied, along with a CN bond-forming reaction, yields the E9 containing synthon shown here, which can in turn be formed by derivatization of proline through a Grignard addition to a Weinrad amide intermediate, followed by an organolithium addition under Falcon-Ann stereo control and acylation. I encourage you to check out the Wei synthesis of viracyne B cited below, which recognized and executed this lovely route, and notice the tactics they applied to overcome the regio control issues encountered in the E9 metathesis reaction. Curvulamine provides a third example for analysis. Identification of the points of high complexity highlights 6 contiguous stereocenters along the bonds connecting the AB ring systems with the CD ring system. Application of Corey's functional group and topological strategies lead to disconnection of the E ring system, potentially via an intramolecular epoxide opening reaction. The epoxide and attendant 2 carbons could be installed via a Corey-Tchaikovsky reaction, potentially an asymmetric one may be developed, or in 2 steps via a Wittig olefination and epoxidation to yield this tetracyclic intermediate which contains the remaining 4 contiguous stereocenters. It makes sense, therefore, to forge the C ring via the synthon shown on the right. At this point, one should evaluate the multitude of potential tactics and relative sequence of steps needed to form these bonds. I'd encourage you to check out the Maimoni synthesis of curvulamine to see which tactics they elected to use to synthesize this challenging target. To finish up, let's analyze picrotoxinin, which I had the pleasure of working on during my PhD in the Shenvi lab at Scripps. Picrotoxinin is a stereochemically dense molecule containing 8 contiguous stereocenters and is topologically complex. It has 5 ring systems, and almost all of the CC and CX bonds present in the molecule are strategic candidates for disconnection. Again, application of Corey's rules, and in particular the structure-goal strategy, is very helpful here, and identifies that 10 of the 15 carbon atoms present are embedded in R-carvone, a chiral pool material, highlighted in this structure in red. Using carvone as a starting material allows us to narrow our search, and we find that what we need to do is derivatize carvone by appendage of a 4 and 1 carbon unit about the carvone skeleton. More specifically, with highly oxidized molecules like picrotoxinin, it's usually a good idea to reduce the molecule's oxidation state to alkene and alkane precursors, a type of functional group strategy which also decreases complexity by removing stereocenters, points of high reactivity, and kinetic instability. Applying this principle to picrotoxinin, we obtain a tricyclic triene, which could be formed with enolate chemistry between carvone and the 4 and 1 carbon synthons depicted here. And I'd encourage you to check out our JACS paper to look at the specific tactics we had to employ in order to effect this synthesis in practice. So, key takeaways and suggestions to improve at retrosynthetic analysis. To review, begin retrosynthetic analysis by identifying elements of high molecular complexity as a precursor to identifying the most strategic bond disconnections. Then, prioritize among multiple strategic disconnections using Corey's strategies. To improve at retrosynthetic analysis, you must of course practice, and my suggestions for practice include to pick a molecule and identify elements of molecular complexity, to build your own routes based on maximizing complexity building transformations and compare your ideas with published syntheses, and to analyze published routes by identifying transformations within them which are complexity building, lateral, or concession steps, considering what might have been done to improve the route. And fourthly, if you're interested in obtaining more quantitative analysis, compare routes and intermediates using Böttcher scores to see what gives the best increase in complexity per step. Thank you for watching, and I'd be happy to answer any questions you might have. Please post your comments in YouTube. I will do my best to answer them. Thank you so much.
Thanks, Stephen, for a great talk, which really brought to life the key concepts of retrosynthesis. Tune in next time as we continue our synthesis module of this course. See you next time.